Apes that can fly. How? Well, not really apes, but flying lemurs are the closest thing. They don't actually fly. Instead, they glide from tree to tree in search of food. And yeah, it works, because these little guys have spent a lot of time perfecting the art of gliding. But their adaptations for gliding aren't what we're talking about today. Instead, we're focusing on another group of animals that took that same ancestral ability and turned it into powered flight. These are the animals that went from gliding to soaring. And there's no better place to look at this evolutionary leap than right here, because this is where it happened. See, all life on land ultimately traces its ancestry back to the water. Almost all modern groups of tetrapods, or four-footed vertebrates, trace their origins to a group called the tetrapodomorphs. And if you want to get even more specific, the group that includes both tetrapodomorphs and fish, called Sarcopterygians, is our particular group of interest. But why focus on these guys? Well, one major group within the Sarcopterygians are the lobe-finned fishes, which are the ancestors of all tetrapods. Lobe-finned fishes are a diverse group that includes lungfish and coelacanths, but it also includes an extinct group known as the tetrapodomorphs, which are the ancestors of all four-footed vertebrates, including us. And the tetrapodomorphs were a diverse group with lots of different kinds of species, many of which were already starting to make expeditions onto land during the Devonian period. But then something interesting happened in the Devonian. A group known as the tetrapods split off from the tetrapodomorphs and began to diverge. For a while, scientists thought that the tetrapods were actually part of a much larger group known as the fleshy-finned fishes. This group would include everything from lungfish and coelacanths to sharks and rays. But recent studies have revealed that this isn't true. Instead, tetrapods are actually a subgroup of the lobe-finned fishes, making them more closely related to lungfish than to sharks and rays. So we know that tetrapods evolved from within the Sarcopterygians, but how did they transition from water to land? It's a big question, and scientists are still working on it. But we do have some clues. As mentioned earlier, some members of the tetrapodomorph group were already making excursions onto land before the Devonian, around 365 million years ago. Take, for example, this one, Elpistostege. This fish had stout, muscular fins with bony supports. That would have made it a pretty good candidate for dragging itself up onto land, maybe to hunt for prey in shallow waters, or to escape predators. But as far as we can tell, Elpistostege and other early tetrapodomorphs were still mostly aquatic. Then there's Tiktaalik, one of the most famous transitional fossils ever found. This fish is famous for bridging the gap between fish and tetrapods. You can see how its rib cage expands behind its pectoral fins like arms. And take a look at those fingers. Yeah, I said fingers. These are modified bony spines that look suspiciously like human fingers. Okay, so you've got Elpistostege, which was a decent candidate for a fish that might crawl up on land every now and again. And then you've got Tiktaalik, which seems like it could potentially drag itself up on land, but neither of these are considered true tetrapods. So what we need is a fossil that shows us the transition from fish to tetrapod. And scientists think they may have found just such a creature. In 2022, a team of paleontologists reported a new species of early tetrapod from the Canadian Arctic. They named it Acanthostega belisi. And boy, do they think it's special. According to the authors, this animal represents a major event in the evolution of tetrapods. They believe Acanthostega was likely fully capable of supporting itself on land, and that it was probably spending significant amounts of time on land. One reason they think this is because of its hands. Or should I say, manus. No, your eyes aren't deceiving you. Tetrapods have two types of limbs. The front limbs are called manus and the back limbs are called pes. We're not quite sure why they split the limbs up into these two categories, but we're glad they did, because otherwise we wouldn't have anything to talk about. The manus had 8 digits, or more accurately, digit-like structures. This is fewer than the more familiar pes, which typically has more like 13. Scientists think that the number of digits on early tetrapods like Acanthostega may have been more like 10, but over time, some of these digits split apart to form smaller bones, increasing the total number of digits on their hands. So if we accept that Acanthostega is indeed an early tetrapod, then we can use it to answer some of our questions about the origin of tetrapods. Like, okay, they had hands, but how exactly were they structured? Well, thanks to Acanthostega, we now know that early tetrapods had more flexible wrist-like joints that allowed them to bend their hands in lots of different directions. This would have been useful for navigating complex terrain, like when they were trying to scuttle up on land, perhaps to hunt or find a mate. Another question scientists were eager to answer was, okay, they had hands, but did they have shoulders? Turns out Acanthostega doesn't have shoulder bones per se, but it does have a pair of large, robust ribs that were attached to the base of its neck. These ribs were likely modified to support the weight of its body as it moved around on land. In other words, these ribs seem to be the evolutionary precursors to our shoulders and upper arms. Now that we know that tetrapods had hands first, and then later developed shoulders, it makes sense that the transition from water to land would have been kind of like learning to crawl. Imagine being able to move your hands and arms in 3 dimensions, but not having any upper body strength to speak of. Having strong pectoral fins would have been important for helping to pull the body forward in a kind of doggy paddle motion. Over time, these pectoral fins would become more sturdy, eventually evolving into legs and feet. Finally, we can ask the question, did they have necks? The answer is yes. Acanthostega had several free-moving neck vertebrae, but it didn't quite have the same sort of neck that we're used to today. Its neck wasn't quite flexible enough to allow for the kind of range of motion that we're used to. Instead, it could only tilt its head slightly up and down. Still, it's a start. And speaking of starts, this is a good time to remind you that this channel starts new videos every week. So if you like what you see, be sure to hit subscribe so you don't miss anything. Acanthostega and its relatives continued to evolve, eventually giving rise to all modern tetrapods. Along the way, various groups split off to become the ancestors of frogs, salamanders, and caecilians, as well as the ancestor of all amniotes. Amniotes are a major group that includes reptiles, birds, and mammals. All amniotes have features in common, including a body that is enclosed by an amnion, hence the name. Amniotes were once thought to be a monophyletic group, meaning that they all shared a single common ancestor. However, recent studies suggest that they may not be a true monophyletic group. Instead, it looks like the various groups that make up the amniotes may have evolved from multiple different branches on the tetrapod tree of life. Regardless of whether or not amniotes are truly monophyletic, it's clear that they represent a successful evolutionary strategy. There are tons of different kinds of amniotes alive today, and they're found in habitats all over Earth. Some of the earliest amniotes were the predecessors of modern reptiles. These animals gave rise to the first true reptiles, which in turn gave rise to the first dinosaurs, birds, and eventually mammals. Of course, mammals also gave rise to humans. So it's arguably thanks to reptiles that we're here today. So there you have it. In a relatively short time frame, evolution went from simple undulatory swimming to full-on powered flight. It's hard to imagine anything happening faster than that, unless maybe we're talking about technological innovation or getting subscribers or views or, things that are important. If you liked this video, you might want to check out another one on how wings evolved. It's pretty great. Thanks for watching.